Hi, welcome to lecture 13 of algorithms. Today we're going to be starting to talk about an algorithmic paradigm called dynamic programming. And so you'll see I abbreviate the term dynamic programming to DP because it turns out that as far as we're concerned in this class, the word dynamic and the word programming are both kind of misnomers for what we're talking about here. So if you see DP, you're welcome to think, oh, that means dynamic programming. But from here on out, we're going to think of this as just DP. Okay, it's the term that we're using is DP. And so the basic concept of DP is something that I want to illustrate to you using a shortest path problem in a graph. So here I've drawn this graph. It looks a little bit crazy. It's a little bit hard to parse. But what we want to do is we want to identify a shortest path from the start node, which I'll circle in green, to the end node, which I'll circle in red. So our goal is find a shortest path. And so what does shortest path mean? Well, it means minimum weight path, where each of the weights of the edges in the graph are written in little numbers by the edge. Okay, so find shortest path in graph from the start node to the finish node. Okay, and we're going to assume this is a directed graph, and all of the edges are pointing this way towards my face. So you can't. So once you're at a particular stage, you can't move backwards. Is the notion here, and so we can think of this, if we like, as a staged optimization problem, where the total cost of a solution is the sum of all the costs we incur in each stage. So we could think of this as stage 0. And so let's just think about what our decision is that we need to make in stage 0. So stage 0 is this. You could think of it as this column, or in this case, there's only one node in the column, so it's just this node. So let's actually zoom in on that particular decision and just see what's going on. So suppose we are at that green node, at the start node. What do we have to choose? Well, we have to choose whether to go up, whether to go middle, or to go down. Okay, so those are our choices. We have 3 choices when we're at the start node. Okay, so once we've made that decision, then we find ourselves in a stage 1 node. So we'll call this column stage 1. Okay, so suppose we've made our decision in stage 0, and now we're in stage 1. Now let's think about what the decision means in stage 1. Well, if we're at the top node, right? So if we're here at that filled in node, we have 3 choices to make, right? We can choose to go up, which means stay on the top. We can choose to go middle, which means move a level down, or we can choose to go bottom, which means go all the way down to the bottom. Okay, and that's true for all these nodes, right? So the way I've drawn this is we have essentially 3 stages, right? We've got stage 0, where we can choose to go top, middle, or bottom. We have stage 1, where we could go top, middle, or bottom, and that's true no matter which node we're in stage 1, right? Where if we're at the bottom, we still have edges connecting us to the top, the middle, and the bottom in the next stage, and so on. And so then in stage 2, we also get to make that choice. And then I'll just note that once we're in this last row, column of nodes, there's no choices left to make, right? So suppose I'm here at this colored in node. There's only one way to get from this node to the end, because I'm making this assumption that this graph is directed, right? All the edges point only to the right, only towards my face. So once we're at the last column of nodes, we're kind of stuck with whatever cost we have going from there to the end. All right, so what does it mean to have a minimum cost path? Well, each of these edges has a number written by it, and just for our convenience, I've written the number on the left end of the edge. So if you look here at stage 0, I have an edge going up with a cost of 1. I have an edge going right with a cost of 2, and an edge going down with a cost of 3. Okay, so this is the full specification of the problem, and the goal is at each stage come up with a decision that gives us a shortest path through the graph. So algorithmically speaking, how would we do this? Right? How would we actually come up with a shortest path? Well, there's various approaches, some better than others. So let's start with one that we will just automatically know is a bad approach. Right? So let's start with an exhaustive search. Okay, so here's our approach 1. Exhaustive search. All right, so how does exhaustive search work? By now, I hope you've appreciated that when I say exhaustive search, I'm leading you to something that's not going to work very well, or it's not going to work very fast anyway, but at least it's going to be guaranteed to give us an optimal answer. So exhaustive search means enumerate all possible answers, right? So actually sit down and write out every single path in the graph, and then pick the best one, right? So the first step is the time-consuming piece, but then if you're keeping a tally of the costs as you go along, by the time you get to the end, you're done, right? You already know, you've already found the best approach. So how do you do this? You enumerate all paths. All paths. All right, so how many paths are there in the graph, right? We know that exhaustive search has to run at least as slow as the number of paths in the graph. Well, let's just think a little bit about what this would be. So at each stage, of which we have 3, there are 3 decisions to make. Okay, so I'm going to make the claim that that means there are 27 paths in this graph, right? 27 different ways to go from the start to the finish. So here's my claim. There are 27 paths in this graph. And my justification is the following. We have 3 stages, and at each stage we have 3 decisions to make. So what that means is that I could imagine writing down the number of paths in this graph with a 3-digit ternary number. Okay, a 3-digit number that can be composed of symbols from a 3-symbol alphabet. Okay, so what is the number of different things, different combinations of things I can write down using 3 symbols, and only 3 of those symbols? Well, it's 3 to the power of 3, right? So this 27 is 3 to the power of 3. Okay, so if you want to think about it like this, if at each stage I only had 2 decisions to make, right? I only had 2 decisions to make, so I didn't have a bottom row. All I had was up and middle. Then I could write down a path using a 3-digit binary number, right? How many 3-digit binary numbers are there? Well, there's 8, right? There's 2 to the power of 3. So if I have 3 decisions to make at each stage, then that means I have to have a 3-digit ternary number, or a number which could represent anything up to 27. So I can generically represent the number of paths in a graph that looks like this as the following. So it would be the number of choices at each stage to the power of the number of stages. Okay, so this is polynomial in the number of choices I have to make at each stage, but it's exponential in the number of stages. So if you imagined making a graph like this that was very, very, very long, this would be, and I had 3 choices to make at every single one, this would be a bad deal, right? This would be 3 to the power of n total number of paths if there's n stages. Okay, so here's, this is a quick and dirty explanation about why exhaustive search is a poor choice for this problem. It's because there's going to be an exponential number of paths, where it's the number of paths is exponential in the number of decisions, in the number of times we have to make a decision. Okay, and then it's polynomial. So for a fixed number of stages, it's polynomial in the number of decisions to make in each stage. But you know, let's focus on the really bad part of it, the exponential part, and you can see that this is not going to be a viable algorithm going forward if this thing is longer than just a few stages. So in the next video, we'll think about ways of speeding this up, right? How could we go faster than exponentially many checks?